Okay, so we were talking about taking measurements. So just to kind of finish the thought here and do a couple more examples. Again, it's really important as we were talking about that whenever you take a measurement, you do look at your piece of equipment as we're sitting here in the lab. When you kind of use any equipment in here, again, essentially, you do want to look at the scale. Now, even the same sort of size equipment, if you will, like a 10 milliliter graduated cylinder that one person is using, may actually have a different scale than what somebody else is using if it was made by a different company. So sometimes the scaling is different and stuff like that. So it's really important to make sure you look at it. As we talked about, there's two main sort of markings that you definitely want to kind of figure out, which again is the large markings. And as I mentioned, usually those should have actual numbers written next to them. And the small markings, which again, as we talked about, there are pretty much the markings between the large markings. They typically don't have numbers sort of written next to them. As we see here, we want to always record, as we talked about, what the certain numbers are. And again, those are always going to be the numbers that there really should be no debate about whether they are. Everybody that looks at it should sort of agree upon that, hey, it is at least that. Again, that uncertainty comes with that first uncertain number, and that's really where the sort of estimation comes into play, where you have to maybe make your sort of guess of where it is. Typically speaking, when we're between two sort of small markings and the difference is just like one or something like that, we kind of do like, okay, like it's kind of half or maybe it's less than half. And sometimes people think they always have to either kind of go like 0.5 or something like that, and you don't. If your marking is really close to the next number, but not really on the next number, you could record something like, for example, 0.9, 0.8, or like I did on the previous one, I did like a 0.4 or something like that because I thought maybe it was less than half. So again, you want to kind of take those measurements sort of correctly. Again, it is important to look at the scale. So for example, if we had something like we were just looking at, like a graduated cylinder, I'll try to draw up high so you can maybe see. Um, and again, we'll just slap our kind of volume right there. So when we look at this particular one, again, we can see our large markings is 10 and 20, just like it was on the previous one. And the difference there, again, is going to be 10 milliliters. The difference, though, when we look at this particular scale, as I zoom in for some reason, when we count the small markings, that is 1, 2, 3, 4, and 5. So in this particular case, there's only 5 small markings between the large markings. So that means that each of the small markings in this particular case is how many milliliters? It is 2 milliliters, right? So 10 divided by 5 is 2 milliliters. So that means that this marking would be 12, this would be 14, that would be 16, and that would be 18. And this makes a big difference when we take our reading now because, again, reading from the bottom of the meniscus, we're now between 16 and 18 in this particular case. What number comes between 16 and 18? 17, yeah? So the best we could actually do in this particular scaling, the way the markings are, is actually to record 17, obviously with our units here. That would mean in this particular case, this would have how many significant figures? So it would have 2 significant figures. The uncertain number in this case would be which number? It is the 7 here would be our uncertain number in this case. And that is because when we have a difference here between 16 and 18, that is too much of a number difference to know, for example, where 16 ends, where 17 starts, right? And that, so it's not like it's just a one difference between the two. It's too hard to know where things are. So the best we could do in this particular case is actually go to the whole number here where we're saying, I think it's 17, but maybe it's 18, maybe it's 16. There's a lot more error sort of associated with this scale than we do over here when we could go, I think it's 16.5, right? So our difference here is like, 16.5, maybe a 16.6, 16.7, a lot less sort of error sort of happening in that measurement. So your degree of goodness in terms of your measurement is based on the scale that you're using, and the equipment that you're using has a big effect at how sort of good or bad your measurement is. This is actually a case where we actually do not go one more place to the right of the smallest marking, because the smallest marking here is actually 2, which is a whole number, and we actually need to take the reading to the whole number. Now, when you take measurements, and what they want you to do here is, as I mentioned, typically speaking, we can't go one more place to the right of the smallest marking, and that's just a good general rule. So I know this is, again, like we saw earlier, to the first decimal place. That usually will tell me it's probably good to take it to the second decimal place. Here, again, this is to the whole number. We could go one place to the right, which tells us we could take our reading to the first decimal place. Again, that doesn't always happen as in this particular case here. You can, and like I said, they oftentimes here will want you, as you continue on in your chemistry career here at Saddleback, they will want you, as you're taking measurements, to actually include what they sometimes refer to as the tolerance of the measurement, or the sort of uncertainty of the measurement. And you could do one of two things to do that, but actually one thing to do that. But what it will also help you is to tell you really how far you should take the reading. So if you for sure hopefully know what the smallest markings represent, you can take the smallest markings and divide it by 2. So if you take the smallest marking in the first example we did, which was 0.1 centimeters, and divide it by 2, you will end up with 0.05 centimeters. And this is what is sometimes included, and they typically want you to include this when you're taking measurements, plus or minus 0.05 centimeters. So if you were to record this, for example, when you're doing an experiment, they typically would want you to write the actual reading that you did, and then next to it do plus or minus 0.05 centimeters. Now, what does the 0.05 centimeters mean? It really is the uncertainty in that uncertain number at the end there. Uh, in reality, most people consider you usually take a reading pretty good, plus or minus 1 of that last number, but there really is a variance. It could be anywhere within that. More importantly, what this plus or minus tells you is when you do it, that is 2 decimal places. That is exactly how far you should take the reading to. So if you are not sure maybe how far you should take the reading to, but you are sure of what the smallest markings represent, if you divide the smallest markings by 2, it will essentially tell you how far you should take your reading to. It works for all these examples. For example, here, if we took the smallest marking, which is 1 milliliter, and divided it by 2, we end up with 0.5 milliliters as our plus or minus. And this would be 16.5 plus or minus 0.5 milliliters. Once again, that is 1 decimal place. That's exactly where we should take the reading to, 1 decimal place as well. It also works for the last one we did, where we don't go one more place to the right. So if we look at for example, the last one, if we take this and divide it by 2, that equals plus or minus 1 milliliter. And that's exactly where we took the reading to, basically the whole number. So if you're unsure about, should I go to like 1 decimal place, 2 decimal places, or whatever many decimal places, but you are sure of, I know for sure these small markings represents whatever they represent, all you need to do is, again, take the smallest marking divided by 2. And like I said, they do want you, typically in lab, when you take measurements, to include that. And again, you would write something like 17 milliliters plus or minus 1 milliliter. Any questions on that there? Yeah. It's sometimes referred to as the tolerance or the uncertainty in the measurement, or the precision. Sometimes people will refer to it as well. Yeah. I think they typically here call it the tolerance of your measurement. Yeah. I'm sorry, say again? This is not in place of rounding. This is just a way that when you take a measurement, um, it is telling you basically how far, based on that piece of equipment, that you can actually take the measurement to. Yeah, we're going to talk about calculations, which is significant figures. It They are tied together, as we'll talk about, but when we do calculations, when we do a calculation is either based on significant figures or is based on decimal places. And it's based on, as we'll talk about, really the least number of significant figures or the least number of decimal places. And really the reason for that is when you do a calculation that's based off of measurements, your calculation is only as good as your worst measurement. And your worst measurement will have the least number of like sig figs or decimal places. Um, and it does have an effect on the actual calculation part that you do. But this right here is technically when you, for example, you're in the lab and you're going to take a measurement, that is what you should write, something like 17 milliliters plus or minus 1 milliliter. What that tells you is based on the equipment that you use, that is the best that you could do in terms of how far you can take it. Now, the more, say, decimal places, significant figures that you could take in a measurement, technically the better the measurement is, right? There's a lot less uncertainty. If we compare this guy, which is basically a whole number, to the measurement we did, say, over here, where we went to 2 decimal places, and in a sense of, how better of a measurement it is, it's definitely a lot better because we could go to 2 decimal places. The error in this number lies in the last number, the 4, which is the second decimal place, right? So that's just a little bit of uncertainty, right? The error in, say, this measurement is 1 milliliter. That's a pretty big room for error. So, for example, what we're saying when we look at this is, I think it's 17, but it could be anywhere from 18 to 16. That's a pretty big room of error. Like you just kind of threw a dart and hope for the best there, right? So there's a lot of uncertainty sort of in this measurement. As you compare it to, say, this measurement, what we're saying here is, I think it's 16.5, but essentially I think it's somewhere in the ballpark of 16.5, 16.6, 16.4, sort of that much error in that one. And again, this would be a much better sort of measurement in the sense of uncertainty than the previous one, because you're able to obviously go to more places and stuff like that. Other questions? Okay. So keep that in mind that when you do take measurements in the lab, and when you do labs in here, in the data table where you will record your measurements, you should include the plus or minus, the tolerance there, just on the measurement parts of it. And again, I'm gonna make you do that because they're gonna want you to do it as you continue on and stuff like that. Personally, you can leave it off, but you should do it just to do practice of it, because they'll expect you to kind of do it as you continue on in the courses here. You do not need to include, for example, the plus or minus part when you're doing calculations. So you just need to do it when you actually are just recording measurements, but you don't need to include it in calculations or anything like that. You'll follow significant figure rules and stuff like that we'll talk about in terms of calculations. Now, one last sort of example, we kind of go back to, like, I'll draw it one more time. Up here, our original sort of scale there, our kind of ruler. And let's just say that we had my arrow this time, like right on that marking right there. And again, this is basically the exact same scale we did on the very first one. Our large markings again here is going to be 1 centimeter. If we count up our small markings, again, we have our 1.1, 1.2, 1.3, 1.4, 1.5. 1.6, 1.7, 1.8, 1.9, and 2. There are 10 markings, just like there was previously. Each of our small markings, again, is the 0.7. Now, in this particular case, we can see it is like dead on the line-ish there. And so we do want to make sure that we record things properly. So if we record 1.3 centimeters, 1.30 centimeters, 1.30000000 centimeters. Is there a difference in how we record our value here? Is there an actual difference? What do you think? The answer is yes, there is a difference. So we'll just start here on the right. That's a lot of zeros. If we look at our scale, we can nowhere near get any of those zeros. So just like putting less zeros, putting more zeros is no good. So this you can't even do that on this particular scale, right? Obviously at 0.1 centimeter for small markings, there's no way you can get all the way down to however many decimal places that is. So we're between these two, and just to illustrate, is there a difference? If we look at 1.3, for example, here, right? This measurement that we take would have how many significant figures? 2 significant figures. The uncertain number, or the estimated number in this case, would be which number? It would be the 3. So when we take this measurement of 1.3 centimeters, what we're really saying is I think it's 1.3, but maybe it's 1.4, maybe it is 1.2, right? When I look at this here, this guy has how many significant figures? It does have 3 significant figures, right? And the uncertain number in this one is a 0. So let's start with, first off, this guy, right? What I basically just said is I think it's somewhere between here and here, right? And clearly, if we look at our scale, we could actually do much better than that, right? That's a pretty big error sort of spot there, right? There's a big room for error in this. Based on the scale that we see, we could actually do much better than this. We can do something like this, which is 3 significant figures, which says, I think it's 1.3 centimeters, but maybe it's 1.31, maybe it's like 1.29. That would be more of this range, right? And if we look at sort of this range, that is more what we actually see, right? That is much closer to where we're taking the measurement from. And by losing the 0 over here, you would not want to do this because you just lost some accuracy there. You lost some goodness on your measurement. For lack of a better description, you just made your measurement pretty crappy. Yeah. It went from being like, I think it's just this much error to I think it's like this much error, right? By losing that 0. So it's really important because of the scale that we have on this particular one, because we have the ability to go to 2 decimal places, we do have to put the 0 in there to preserve the proper number of significant figures in our measurement, and frankly, not make our measurement worse than it should be based on the equipment we're using. So sometimes people, if they hit an exact number, will just kind of lose a 0 here or something like that. And when you're doing that, which again you're doing is making your measurement a lot worse than it should be based on the equipment that you have. So the proper reading should be this one. You do need to put the 0 in there to maintain it. And if you weren't sure, again, you could go back to our, I'm going to divide this by 2, plus or minus 0.05 centimeters. That is 2 decimal places. That is where I should take my reading to. So again, you could use that sort of tolerance, plus or minus, to figure out how far you should take the reading. So it's really important not to do either of those things. By putting more zeros in, for example, the first one I crossed out, we're actually saying our measurement is way better than we could do on the actual piece of equipment that we have. By losing zeros, we're actually going a lot worse of a measurement than we should have with the equipment. So you do have to try to make sure you always give it to the right number of significant figures. Again, that may require you to add a 0 to get yourself there. Any questions on that there? The other type of thing that you very commonly come across when you take a measurement or anything like that is sometimes you do use digital sort of displays. So displays digital, for example, the balances in the back of the room, the scales, those are all digital. Whenever you use anything that is digital, you should always record all the numbers that are there. That's because they wouldn't be on the screen if they weren't important. So you should always record all the numbers. That is a very common sort of error that people make. For example, they'll go back there and it always amazes me. Everybody always weighs things exactly to the number, like 54, always no decimal places, nothing like that. It's actually quite hard to get it to exactly the number without taking a lot of time and stuff like that. So even if you are 59.000, you should record all those zeros in a digital situation as they would be significant and they would be important as well. So keep that in mind as well. Any questions on that there? Okay. All right. So as I mentioned a second ago, the reason we record all the certain numbers plus that first line of certain numbers is that essentially what significant figures are. Significant figures, essentially, as you could probably guess from what we were talking about here, they come from measurements. Yeah. So significant figures come from measurements. No drinking in here. Put the water away. Yeah. So let's talk a little about accuracy and precision when we take measurements. Accuracy tells us how close the value is to the true number. So if you're really accurate, that means that you hit whatever the true value should be. You're very close to it. Now, precision, on the other hand, tells us how close a set of numbers are to themselves. So to illustrate this, for example, if we were to throw some darts at a dartboard, right, and the goal here is to sort of hit the bullseye in the middle. If I take my 3 darts and I throw it and I go here, maybe I missed the board there, or a bad shot. Am I accurate in this case? I am not, right? Because the goal here is to hit the center, right? Am I precise? I am not precise because I am all over the place, right? I include and hit somebody standing next to the dartboard, right? So I am neither accurate or precise in this case as they're all over the place. So I take my darts up and go, cool, we'll just do like a double or nothing type situation. Why not? So I take my darts and I throw them again and I go boom, boom, and boom. Am I accurate? I am not, because again, the goal here, right, is to hit the middle. Am I precise? Yes, I am precisely not accurate, right? So you could have a good level of precision, but you can be not accurate as well, right? You can, as they say, do the same thing over and over again, but do it wrong every single time the same way, right? And you'll get the same result, right? So you can be very precise, but not very accurate. We oftentimes will use precision, for example, in experiments where we do multiple trials. So we repeat the same experiment over and over again. The idea there is to figure out, precision and is the experiment reproducible. So I pick up my darts and I throw it for a third time here. And I go boom, boom, and boom. Am I accurate? Yes. Am I precise? Yes. And that is really the goal, right? When you're, for example, doing experiments, is you do want to be accurate and you also want to be precise. You want to kind of get the right answer and you want to be able to redo that experiment multiple times and come up with the same right answer every time, right? You want the reproducibility of an experiment. Any questions on the difference there between it? Here's our dartboard. So again, we can see here, much like my example, all over the place in the first one, not accurate, not precise, kind of precise there, but definitely not accurate. And again, accurate and precise. I think I almost picked the same colors. Look at that. No, that's bad. All right. All right, so take a moment here and decide based on this what the proper reading should be. I apologize. The numbers obviously should go to these guys here. They're just to the left there, it looks like. So, all right, what should be the proper one with its tolerance there? Where this. Okay, so let's take a look. Again, we want to look at our big markings here. So our large markings is going to be 1 centimeter. If we count the little markings starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10 markings, which means here, each of our small markings is going to be 0.1 centimeters. We already know our tolerance here, by the way. We could divide that by 2, and that will give us plus or minus 0.05 centimeters. So that almost should get us to the right answer right about there. But again, this would be 2.5, this number. This guy right here would be 2.6, and this guy right here would be 2.7. So the error does look like it's between the 2.6 and 2.7. Is definitely 2.6, which we would want to write. And again, we do have to take an estimate here, and they felt it was very close to the 2.7. And you can see they recorded the 9 here as our uncertain number, and centimeters plus or minus 0.05 centimeters in this particular case. This would have 3 significant figures. And again, on this particular scale, we can go to the second decimal place. Letter E is incorrect based on the tolerance here is obviously too far based on the scale. That's 3 decimal places, which you cannot do. Question on that one there. All right, so do the red one, same deal. These guys go right about there. Okay, so once again, this is basically the same scale we had on the previous one. So our large markings, again, going to be 1 centimeter. Our small here will be 0.1 centimeters as we have 10 markings. And again, we could divide that by 2 and get our plus or minus 0.05 centimeters. So really, again, by dividing that by 2, we know that we definitely should go to 2 decimal places when we take our reading. Again, the red line arrow is just beyond the 9, so we definitely would record the 9 as a certain number in this case. This first little dash here would be 9.1, so it's definitely not 0.1. It's less than that. And now we got to decide kind of, we know we could go to our second decimal place. How far in is it? And again, it does look pretty close to the 9, so it's not too far in. So they did go, I believe, with 2. Again, centimeters plus or minus 0.05 centimeters. So it looks like C would be a winner in this situation. Obviously, it can't be 9.15 because that would be to the right, obviously, right, of the first marking there. So it is before that. So we do have to put the 0 and the 2. Any questions on that there? All right, so meniscus here, right? So this is like a graduated cylinder. So why don't I'll just kind of zoom in on it. Why don't you take a proper reading of what the volume should be in? Okay, so looking at this, again, we have a liquid in a glass container, so we have our meniscus there, and as we talked about, for the most part, you can go bottom of the meniscus there to read it. We still want to do the same thing, so we could definitely see our big markings here, 30 and 40. So our large markings, right, again, it's going to be 10 milliliters in this case. That is the difference between those two numbers. If we sort of count up our small markings, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we do have 10 markings, and that means that each of our small markings in this case is going to be 1 milliliter. So this would be 31, 32, 33, 34, 35 on that line, 36, and 37, 38, and 39. So once again, we would record our certain numbers, which in this case, it does appear to be above the 36. So we would record our 36. By the way, again, if we're not sure how far we could go, we could just simply divide that by 2, and that will give us a plus or minus 0.5 milliliters. So that does tell us in this case, we do need to go to 1 decimal place, right? And in this case, it maybe looks like it's halfway there. So we'll record 0.5 milliliters plus or minus 0.5 milliliters in this particular case. The uncertain number, once again, here is the 5 at the end there, the 0.5 basically. This guy is our uncertain number. These are our certain numbers. This number, again, would have 3 significant figures. Yeah. Any questions on that reading there? Hopefully they agree. Let's see. There we go. Oh, they went 8. They felt it was a little bit bigger. See, that's where the estimate is. All right, I blew it up. It looks halfway there. But 36.8, again, it does go to 1 decimal place. And again, that is where the uncertainty lies in that measurement. All right. Now, another very common piece of equipment that we use in chemistry, and we'll use in this class, you use it in all the rest of your chemistry classes as well. This is actually what's known as a burette, and this is a burette, which is really a device that's used to deliver a very accurate amount of volume It is a little different in terms of how we read it and how the scale is. So when we use a burette, we do fill it actually from the top, use like a funnel. We fill from the top and it comes out the bottom basically. So it comes, fill at the top, comes out the bottom. When you look at the actual scale on a burette, and I'll just kind of do the top part. At the very top where you fill it is actually the zero marking. And then it goes one, and then it goes two. It actually increases as you go down. So you do want to be careful when you use a piece of equipment. Sometimes things are numbered in a different way. That means, for example, if I had a liquid kind of in this area, this actually would be 1 point something and not two. Yeah, so it'd be 1 point something. It's also a very common mistake people make is they fill up their burette to the very top and say it's a 50 milliliter burette, they'll record 50, and you should never do that. So you should always record, for example, when you're using a burette, the actual number that it says where the volume is. So for example, if I filled it all the way to the top, I should record zero, really 0.00. That is what I should record, and I shouldn't record like the whole thing's 50 milliliters in there. Otherwise, you will definitely get the wrong sort of thing. So if we just kind of blow up on this guy again, we are actually, once again, increasing as we go down. So we could still do the same thing. That is a large marking. That is a large marking. So our large marking here, once again, is 1 milliliter difference between it. If we count our markings here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, we have 10 markings. That means each of the small markings in this case is going to be 0.1 milliliters. So this would be 28.1, 28.2, 28.3, 28.4, 28.5, 28.6, 28.7, 28.8, 28.9, and 30, 29 there. So if we look at our meniscus, it's in this area-ish, I think, the bottom. So we can see that it is at least 28.8. And those are the certain numbers, right? Once again, if I take this small marking divided by 2, it automatically tells me I should definitely take this reading to 2 decimal places. So again, these are our certain numbers. Our estimate here, wherever you think it may be, maybe think it's a little bit lower than half, maybe go 6 or something like that, and milliliters, plus or minus 0.05 milliliters. Again, that is going to be our uncertain number in this case. This number would have 4 significant figures as well. So it's really important, especially if you have something like a burette, and again, it starts at 0 at the top and goes larger as you go down, and you're emptying down. You got to make sure you adjust. So very commonly people read it sort of the wrong way. Any questions on that there? All right, I think I just want to kind of get through just a few more examples here. So that was good. We will lay up the lecturing for now.